In this video, we're going to learn about a concept called linear independence and what it means for a set of vectors to be linear independent. So first off, the definition. A set of vectors is considered linearly independent if whenever you have a linear combination of them giving you the zero vector, the only way for that to happen is if all of the constants are equal to zero. So again, the idea is you can take these vectors and you can combine them with different constants, and then you ask yourself, okay, how could I get zero as the answer of this? And if the only way to get zero on the answer is if all the constants were zero, then they're called linearly independent. And if there's any way to get zero where the constants are not all zero, then they'd be not linearly independent, or sometimes we would call that linearly dependent. Now, for this first example, we have these two vectors here, and I'm claiming that they're linearly independent. And the way I know that is if I do C1 times the first one plus C2 times the second one, and I said my answer was 0, 0, and I wanted to see how this could happen, I would write out a system of equations. 2C1 plus 5C2 is 0, and 3C1 minus C2 is 0. And if you were to solve that, you're going to get that C1 and C2 both have to be 0. And so that means the only time that you can get 0 as a combination is if all the constants, in this case both of them, are 0. Therefore, they are in fact linearly independent. These next two vectors, 2, 3, and 4, 6, they are not linearly independent. And we can see that by saying 2 times the first vector minus 1 times the second vector gives you, in fact, 0, 0. Therefore, the combination where my coefficients are 2 and negative 1, which are not just 0, gives me the output 0, 0 here. Therefore, that means that they are not independent. Again, we also call that linearly dependent. Now we can do the same thing with three-dimensional vectors here. So I gave you the vectors 1, 2, 3, 4, 5, 6, 7, 8, 9, and I want to see whether they're going to be linearly independent or not. So again, we could do C1 times the first vector plus C2 times the second vector plus C3 times the third vector. Set that equal to 0, 0, 0. Then if I go ahead and write out the component equations, I'd have C1 plus 4C2 plus 7C3 is 0, and 2C1 plus 5C2 plus 8C3 is 0, and 3C1 plus 6C2 plus 9C3 is 0. If I put that into a matrix format here, and then I'm going to do my row reductions here. Now to save room, I'm not going to do all the individual steps here, but you can work it out on your own and see if I get the right answer. I'm actually using my calculator to do all the work for me, and I'd recommend seeing how to do that as well on whatever calculator you have. It's probably not going to be too bad stepwise in there. But regardless, I'm going to get this here, 1, 0, negative 1, 0, 0, 1, 2, 0, and 0, 0, 0, 0. And what we're going to see from this is that we actually have infinitely many solutions. If I write out x minus z is 0, that means x is z, and y plus 2z is 0, y is negative 2z. So something like 1, negative 2, 1. So maybe 1 times 1, 2, 3, negative 2, 4, 5, 6, plus 1, 7, 8, 9. And this should give you 0, 0, 0. And so since I found one way that gives me 0, where the constants are not all 0, that means they are linearly dependent. So again, you want to be able to be given vectors and determine if they're independent or dependent. And you do that by setting up a system of equations and solve for it and see what you get, if there's an answer that's not just 0 or not. There are some shortcuts depending on specific situations. For example, determinant can actually help you answer this question as well. I'm not going over that right now because it doesn't work on every problem, and you should know the general process here. But if you want to read up in the book about the shortcuts, that's fine. And now that we have linearly independent, we can move on to the next topic, which is called a basis. And a basis is a set of vectors that has two things. It has to be independent, and it has to be spanning set from the previous video. And so as long as it has both of those things, it is going to be a basis. And then we get the nice terminology here. Finally, you understand what dimension is going to be. The dimension is simply the number of vectors in the basis. So for R2, the set 1, 0, 0, 1 is a basis. In fact, it's called the standard basis. And so that means R2 is two-dimensional. That's why the 2 is there. If you wanted to do R3, that would be 1, 0, 0, 0, 1, 0, 0, 0, 1. And that means that R3 is going to be three-dimensional, or 3D. If I look at 2 by 2 matrices, this is going to be your standard basis for it, these four matrices here. So therefore, M2 by 2 is dimension 4. And the last one here is P2, the set of polynomials degree 2 or less. The standard basis for that is going to be x squared, x, and 1. And so therefore P2 has dimension 3. And you can talk about dimension of any vector space you come across. You can talk about dimension of subspaces. And you can do a whole lot of information based on the dimension.